All right, friends who live in Europe or friends that have visited Europe, especially in the summer, do you ever feel frustrated that the HVAC systems they have there is just kind of insufficient? You know, you get into a building, it feels a little stuffy. Why is that happening? Well, a lot of them aren't using dehumidifiers, and it's actually for a good cause. They don't want to use the extra energy that causes carbon gas emissions that's bad for the planet. Well, ETH Zurich, their researchers, they want to make sure that we can have comfort and love for the planet all at the same time by building these walls that can passively absorb humidity. So if you like being comfortable in a building and you love the environment, well then let's just get into it. You know, it's honestly kind of surprising that we love additives so much, yet I can't remember the last time we talked about something 3D printing. I feel like it's been like 3 months, 4 months now. Yeah.
We need to give more attention to the additive world. And I'm not just talking prototyping. We're talking production.
We're talking production, because last time we talked about it was, I think, the Audi episode where they were doing jigs and stuff. Yeah.
It may be.
Well, we're gonna switch it up today. We're gonna give the fans, which includes us, what they've been asking for in their hearts for the last couple months. And that's another additive episode. And
let's go, baby.
With ETH Zurich, which is always a pleasure to visit, we're looking at dehumidifying walls. And this is the theme of topics you see more in Europe than you do in America because they're so energy conscious. I remember a while ago, probably 2 years ago at this point, we were talking about passive HVAC, like buildings that open and close and using the pressure just make air move around the building instead of having to turn on the AC in the summer. Well, another component of feeling comfortable in a building is humidity, right?
Well, and potentially even more so than the ambient temperature in the building, especially in the summer when it's hot. The ambient, or the relative humidity rather, that plays a bigger deal into people's comfort. Sometimes, you know, changing the humidity by a meaningful amount can improve people's comfort a lot more than dropping the temperature by 1 or 2 degrees.
Dude, absolutely. When I'm in Florida and it's 75, I can't wait to leave. Now, when I'm somewhere where there's dry heat, like let's just say California, and it's 80, I feel perfectly fine. I don't know if that's just me, but I feel like a lot of people feel that way.
No, I'm with you, and especially indoors.
Yeah.
Like, I don't know why, but like when you're fully dressed and you're in an office, or I'm thinking about like you're waiting in the line to get like in and out of a theater or a museum and it's packed and there's lots of people and you see like the windows fog up because it's so humid in there. Like that's one of the most uncomfortable human experiences, right? It's highly uncomfortable. And I think Europe is definitely a pertinent application because the use of it, like, I guess
HVAC?
not HVAC in general. They generally have cooling, but not AC. The use of AC is like, it's so much higher in the US than it is in Europe. But the reason why Europe is so conscious about this is because the ventilation systems consume energy and contribute to emissions. So the new approach is basically to try and find a way passively, without actively requiring extra energy or extra emissions or even flipping the switch to turn something on. Can we use the natural properties of a material to absorb moisture and then release it when it's ventilated, essentially doing dehumidification without spending a bunch of electricity to do it?
And that's an important call out. ETH Zurich is a university in Switzerland, and Switzerland has a goal of being, I think, net carbon negative or net carbon zero by 2050. So like all of this is pretty aligned with the nation's goals. And you're right, like if there's a way to passively do it, especially via materials that we use a lot in the building for walls and other structures, then that's just a win-win because it basically comes free whenever you set up a structure. So that's exactly what these folks at ETH Zurich have been trying to tackle. Like, can we set up a way to passively do this and not incur additional carbon cost? And they, like, keeping that theme in mind, they were like, can we actually leverage waste material? And where that led them to was marble quarries. They realized that they could take all the waste that's produced and grind it up really finely and then use a geopolymer to bind it all together, essentially creating cement, like a cement-like structure, to create a porous structure that can absorb and at least temporarily hold on to humidity. Now, this is interesting, not just because of the material science side of like what they're cracking here with the two materials used, but they also brought in 3D printing, which again, we love, to develop these microstructures that's like a part of their secret sauce that's helping them absorb the extra moisture in the air. And the approach that they're using is not like FDM, which is fused deposition molding, where I think most folks listening, that's probably what they're familiar with, but that's what they think of when we say 3D printing. When there's concrete buildings being made, you squeeze out concrete, you lay it on top of each other. When you're using your plastic 3D printer at home, it's laying down layers and layers of plastic. With this binder jet approach, which I think we talked about before for creating dental stuff.
Yeah, I think
you basically lay down like a powder, a material of some form, and then you put on a binder over it that brings everything together. Now, we've talked about cement probably a handful of times on the pod, but the process to create cement actually creates CO2. This, very similar to cement, also generates CO2, but not as much. So that's already a bit of a win in comparison to a different commonly used porous material for construction.
Well, and just to highlight the binder jetting process, because you mentioned the two main ingredients before to kind of drive that point home. So you talked about like the marble powder, which is the waste material from quarries, right? They grind that up really fine. That's what they call the bulk. The bulk is the bulk powder, like a layer of powder, basically, that's been deposited and then sitting there waiting to be bound together. And then the geopolymer you mentioned, which is the potassium silicate, that's what solidifies the material. So essentially, you've got a bed of powder laying there, and then you're selectively applying glue that helps hold it all together. And then you lay down a new layer of powder, and then a new layer of glue, et cetera, et cetera. And you do that repetitively, and you add up a bunch of layers, and then it creates this 3D structure where essentially wherever the glue was applied, the binder, it's helped form the powder into a part of the solid 3D structure, and the rest of the spare powder can be shaken off and reused.
Yeah. And, they created a proof of concept structure for this to show that it can be done. It's relatively small. It's about like 10 square inches and 2 inches wide to just show what like a wall like that could look like. But the bulk of proving the capability of this device or this product is from simulation. So their team ran a simulation, and before doing that, I think it was funny you were talking about discomfort indoors. They characterize that by saying, hey, indoor humidity of like the comfortable bounds are like 40 to 60%. Anything outside of that can be uncomfortable. So they created a discomfort index to then gauge like at one point humans become uncomfortable in a given scenario. And then in their simulation, they ran a traditional, building with painted walls versus their wall material. And the TLDR, the summary of that is walls that are about 2 inches thick can reduce the index readings by people inside by about 70 to 85%. By 75%. And then a little bit more than 2 inches, you're looking at 85%. So that looks impressive. Again, this is all just simulation. And then the next bit that I think is probably most relevant to the researchers, given that their goal was to reduce the carbon emissions, is that over a 30-year lifespan, the greenhouse gas emissions associated with the creation of this product and its operation is going to be less than the conventional approach that we use a dehumidifier, for example, with our HVAC systems. Now, I have some opinions about that, but I want to get your thoughts on this because I'm curious what you think.
No, I think it's definitely interesting. I would love to see it. I don't know if I'm just like a doubting Thomas here, and I just want to see it myself or experience it myself. But I understand the approach here where they made a scale model, they put it inside a controlled environment, and they understood how much it could affect the relative humidity. And then they simulated this in a public library reading room. it's awesome that they think the panels can reduce discomfort by 75 or 85%, depending on how thick the panels are.
Mm-hmm.
I would love to see this in practice. Honestly, looking at it, it looks like the geometry is actually kind of cool. Like, so if you played into it and like made the 3D printed geometry part of the interior design, you could easily find a place that's willing to adopt this. I know that there are some CO2 emissions here, but I trust that over a long period of time of people relying on this, that it would overall reduce the carbon footprint. My hesitation here, though, is like, do people actually feel the difference, and how quick do they feel the difference, and how resilient is it to things like temperature changing or things like 25 people being in the room instead of 15? I think for them to be able to sell interior designers and contractors and architects, people designing and building new buildings, they're going to need some more proof of concept than just a simulation. That's where my head is at mostly. Is like, I love the idea. I love the execution so far. I would love for their next step to be like, all right, we found the library at our school is willing to use these panels, and we're going to see if it makes a difference.
And to give them credit, right? They said where they see this being applied is actually in situations where the conventional approach is already being utilized, but it's just not capable of, sustaining it for whatever level of occupancy.
Yeah, basically helping close the gap.
Exactly, closing the gap. So that makes sense. And then they said that they believe this is a technical demonstration that it's possible. And now they want to work with industry partners to, scale it up and make it a product that can actually be commercialized. So that's great that they're conscious of it. Some feedback from me as I was going through this, it seems like the 3D printed aspect is critical to this process, but just definitely does not scale, right? Like the binder jet printing that you do to make a retainer, it's a product. You make it once or once every year. It's not massive. For things like that, you can mass produce it, and there are companies built around it. For something like walls, just imagine like you're creating new structures left and right, or even if you're retrofitting, there's a lot of area to cover.
I wonder if they end up having to create their own bespoke binder jet 3D printer that's big and with a large enough build volume to be able to do
maybe
this. I don't know.
But if accuracy is a concern, then you're still, I don't know. 3D printing technology is advancing by the day, but the bottleneck will be, your layer height and how fast you're actually going through to process all that.
Yeah.
Then there's the issue of within 30 years, this comes out better in terms of greenhouse gas emissions and the conventional approach. My question there is, what is the actual payoff? Like, do you start breaking even at year 23? If so, like, does this really make that much sense? You know what I mean? Just given like how much buildings change, et cetera, et cetera. And then lastly, like practically, would anyone actually want this to be a part of their wall? Because
that's kind of goes to my feedback, right? Like you have to go test it, see if people like it, see if it works enough to sell people on it.
I think this would be a cool thing for like those dynamic art installs that you see. I don't know, it could be interesting to like make a statue out of it and then be like, oh, by the way, this filters the air for humidity. I'm just not totally sold on it. But I am excited to see what happens when they start working with these industry partners to work out some of the kinks and see if it can scale or not.
Yeah.
And more importantly, I love a good moonshot. I like the fact that they're trying something different in this space.
Yeah, and I'm with you. Like, if your goal is not to completely replace traditional ventilation, but it's to help close the gap, let's say, and in uncomfortable situations, or reduce energy spend in humid situations, I'm wondering if it allows people to get like extra years of life out of an old system. Like maybe there's additional carbon emission paybacks that aren't being considered here beyond just the material itself. I could see a library not having to pay to upgrade their HVAC system if they're able to install a bunch of these panels and they're able to keep using what they're using without extra energy spend, or again, the carbon required to manufacture the new ventilation system that would have replaced it.
Yeah, that's a fair point. The last thing I was going to say that I just remembered, I I think mostly in the US, our walls, they are technically load bearing, but the material that goes on top of the studs, the drywall, is not. It's the studs that are doing the heavy lifting. Mm-hmm. I think in Europe, it's mostly brick buildings where the material itself is load bearing, right? Mm-hmm. So I think if you're retrofitting, that's another thing to like kind of keep in mind is that what kind of additional supports have to be built in now that you have a material that is likely going to be worse compressive strength than the traditional dense brick that was there before.
That makes sense. And maybe they're just like plastering it over the bricks. Who knows?
That's a fair point.
But yeah, one thing I did want to throw them a bone on the 3D printing part because I feel like we kind of went hard on that. It looks like they're printing the macro structure, not the microstructure, if that makes sense, right? I think the microstructure is based on the porous microstructure of the marble powder. Mm-hmm. They're not 3D printing the microgeometry that is, what is it called? Hygroscopic, right? I don't think they're printing the moisture absorbing microstructure. They're printing a macrostructure that creates a lot of surface area for this powder per unit volume. So there may be a future in which they're able to do things like, I don't know, injection
like
mold
having
this.
molds. Yeah, maybe. Yeah,
because 3D printing is like definitely something awesome here for prototyping concepts. And even for low to medium volume. But I wonder if there's a way where they can either increase the layer height a bunch because they're just printing the macro structure, or like we said, even go straight to pouring it into a mold. I don't know.
Yeah, that's a fair point. All that to say, if you care about humidity and you don't want to be humid inside a building, but you also don't want to contribute to greenhouse gas emissions because you're using a dehumidifier in your building, well, then these folks at ETH Zurich might have an answer. They are trying to use a porous material built from marble waste to create these walls that can actually absorb the humidity in an environment and store it so that your HVAC system doesn't have to do the heavy lifting. And it might just help Switzerland meet their net zero carbon emissions goals by 2050.
Boom.
Money. All right. That's the pod.
Peace.